Hello everyone, my name is Matt Duddy. I am a grower and provider of Narcissus bulbs here in western Pennsylvania. As many of you know, I manage a website, daffodils.com, where we host an annual selection of popular and specialty daffodils. I graduated from Penn State with a degree in chemistry and also from the Katz Graduate School of Business at the University of Pittsburgh with a master's in business administration. The focus of my presentation today is viruses in Narcissus. It's a topic rarely discussed in polite company, and most enthusiasts would rather not know about it. But as a provider, it has become my business to know. And I'm here to share a few things that I've learned about this after years of working on it. Numerous studies have been conducted into the prevalence of viruses in Narcissus populations, both in the wild and in people's gardens or collections. Perhaps one of the most succinct is entitled Narcissus Plants, a Melting Pot of Potyviruses. Several other studies have shown that approximately 66 to 100% of Narcissus plants are infected with one or more potyviruses, the most common type of virus in Narcissus. In fact, several potyviruses affect Narcissus. The most frequent are Narcissus late season yellow virus, Narcissus yellow stripe virus, Narcissus degeneration virus, and Narcissus white streak virus. And there are others, as well as unknown poty-like viruses. In addition to potyvirus and friends, daffodils are also susceptible to cucumber mosaic virus, a bromovirus. Infected plants typically show no symptoms, aside from diminished growth. Narcissus leaf tip necrotic virus is a tumbus virus, a family that typically infects tomatoes. As the name implies, leaf tips of infected plants turn brown and die. The symptoms are often misattributed to early frost damage, but occur even when the plants are grown in the greenhouse. Curiously, this virus does not infect tomatoes, despite being from that family. Its only natural host is Narcissus plants. Color breaking in reverse bicolor daffodils is caused by Narcissus mosaic virus, a potex virus. Infected plants show no symptoms, not even diminished growth, except that yellow petals break up into patches of color. This can be apparent when the flower opens or as the blossom ages. Narcissus latent virus is from the machlorovirus family and is known to infect both wild and domestic plants worldwide. Symptoms are not typically apparent and may be limited to chlorotic leaf tips. Lastly, and perhaps my favorite, is Narcissus symptomless virus, a carlavirus. Like cucumber mosaic virus, infected plants appear healthy, but over a period of years, they seem to die out. There are at least two other carlaviruses, including Narcissus common latent virus and Neurine latent virus. With the exception of bromo and tumbus viruses, all of these viruses share a similar structure, being single-stranded, positive-sense RNA viruses. Tumbus virus and bromovirus, in contrast, are monopartite and tripartite viruses, respectively. Totally different structures. My objective then was to develop a process to eradicate the widest possible range of viruses. And this similarity in structure is the key. In the field, viruses are spread by aphids and possibly by mechanical contact of wounded plants. Some of these viruses are also readily transmitted through cultivation practices, such as chipping and twin scaling, which is a problem for producers, such as myself. Any virused bulb, when propagated, will produce more virused bulbs. Worse than that, any healthy bulb cut with the same blade as a virus bulb is now an infected bulb. Thus, one infected bulb can spread the virus to hundreds of chips. Obviously, this is not in our interest. So I began searching for an answer to this problem. The most obvious route was to use virus-free stock, plants that looked perfectly healthy, with no signs of virus at all. So I ordered potyvirus test kits from Agdia, as well as tests for CMV, and began systematically testing cultivars in my garden. My objective, again, was to find healthy propagation stock. But what I found, however, was consistent with some of the first studies that I had cited, an infection rate of about 80%. Remember, I selected healthy plants, plants with no visible symptoms at all. Thus, Narcissus plants can be infected with viruses and show no real symptoms. There are symptoms, however. In every paper where virus-free plants have been obtained, the authors espouse the characteristics of healthy plants. The leaves and stems are taller. The bulbs divide faster. The flowers last longer. Overall, the plants are more substantial, withstanding harsh weather more effectively. In several measurable ways, the plants are improved. Because I did not have any real success at selecting virus-free propagation stock, I was forced to take a deeper look at this problem. As many of you know, I work closely with Mr. Joe Ham. For the past 3 years, I have been copying his collection to my farm in Volant. Everything we get from him is chipped and placed in a dedicated bed. And since we are receiving hundreds of varieties from him every year, a solution to this problem became urgent. Several methods of virus eradication in Narcissus have been attempted, including by electrotherapy, thermotherapy, and chemotherapy, all with varying levels of success. One study reports a success rate up to 80% based upon bulbil regeneration alone, although not everyone in the community accepts those findings. In plants, chemotherapy is accomplished through treatment with various chemical agents, such as ribavirin, an antiviral compound, salicylic acid, hexanoic acid, and atomic silver. All have been investigated for virus eradication in plants, and some are used routinely. For my first attempt at achieving virus-free plants, I repeated the essence of one particular study, that of Sochacki and Orlikowska, but with my own twists. All of the papers required tissue culture as part of the process, but I didn't have a lab. So in order to do this work, I refinished my basement and installed a lavishly equipped tissue culture lab. I crafted a series of 10 experiments, applying combinations of proven methods of virus eradication, including bulbil regeneration, electrotherapy, ribavirin, silver nanoparticles, hexanoic acid plus melatonin, copper sulfate, and zinc oxide. After months of study and delighted by my new lab, I was eager to start the work. Almost immediately after starting, however, I ran into a wonderful problem: mold. Several of the papers upon which this work is based referred to fungal contamination, and in one case the work had to be entirely repeated with new disinfection methods adopted. It has been shown that mold lives inside of the plant tissues and is thus not suppressed by surface disinfection and sterile conditions. It took me 7 attempts to definitively solve the mold problem. With the mold in the rearview mirror, I performed my 10 experiments, 10 plants each of 4 cultivars, for a total of 400 explants. Of the 10 experiments, some were found to be impractical and were quickly ruled out. On the first run, I found out that my concentration of silver nanoparticles was excessive. So I cut it down to 1/8 and repeated 6 of the experiments. 4 of the 6 seemed workable and also successfully yielded bulbils, which were then subcultured. Still, the regeneration rate was not wonderful. In the first year, most of the bulbils came up, producing short, thin leaves. I had 8 virus test kits left, so I selected the 8 best-looking plants with the biggest leaves. I had to trim the leaves all the way down to the base in order to get enough material for the tests, which was hard. I'm trying to get these to grow faster, and clipping doesn't help. All 8 were from 2 experiments and tested negative for potyviruses. So, we have virus-free plants. Despite achieving this for the first time, I wouldn't characterize it as great success. The process is slow, laborious, expensive, and prone to total loss. I needed a process that I could use in real time. For the past decade, we have been chipping. It's easy, fast, forgiving, and has a high rate of success. I wondered if it would be possible to apply the principles I had learned from virus eradication in tissue culture to our traditional process. After some thinking about it and another look at the papers, I developed a process to achieve the same results but on a much larger scale. The overall process is faster, easier, less expensive, and has a high degree of success. Still, it's technical. The overall process is as follows. First, we hot water treat everything. 44.4 degrees Celsius for 3 hours, with formalin. When it's time to propagate, the bulbs are soaked in fungicide for a few minutes, and then cleaned of roots and leaves. They're chipped in the normal way, longitudinal cuts, each containing a piece of the basal plate. For this to work, it needs to be a complete plant with both leaf and root tissue. Although we typically use smaller bulbs for chipping, every now and then we might find a flower inside. After cutting, the chips are rinsed 5 times to remove excess mucilage. Next, the chips are loaded into an electrophoresis tray. An electrolyte solution is poured over the chips, which should be fully submerged for best results. The liquid and the gel share the same concentration of electrolytes, ensuring even electrical current through the sample, our chips in this case. The chips receive 20 milliamps for 20 minutes, the optimum value from studies on Narcissus, gladiolus, and potato. After electrotherapy, the chips are rinsed 5 times to remove the electrolyte solution and placed into a plastic bag. The next step in the process is chemotherapy. Chips are soaked in a solution of silver nanoparticles for 12 to 24 hours. To minimize the use of solution, the bags are perpetually flipped such that half of the chips are submerged half of the time. When the treatment is finished, excess solution is drained off and the chips are allowed to rest for 3 to 4 days. From there, the cuttings must be incubated for 8 to 12 weeks. Unlike traditional chips, treated cuttings are more sensitive, having been subjected to electro and chemotherapies. For the incubation phase, chips are immersed in fungicide and then planted in damp vermiculite. We use 12-inch square gusseted bags, which can accommodate about 200 chips. Roll, staple, and store in a cool place for 8 to 12 weeks, ideally at 68 degrees Fahrenheit. By November, the chips have developed roots and tiny bulbils. At that point, they may be planted in the ground with about an inch of loose soil on top. An extra inch of mulch helps keep the moisture in during dry winter months. My first large-scale application of this process was last year. We treated 300 cultivars and produced over 40,000 chips. Since each chip makes an average of 2 bulbs, That would be 80,000 bulbs in 3 or 4 years. However, we had a desiccating winter last year, and at one point the temperature was minus 12 degrees Fahrenheit. As a result, there were losses, from 30 to 50% in some cases, and a handful were totally lost. Therefore, I recommend incubation and mulch. The opportunity to assess the virus eradication success rate passed me by in the first year, which was last spring. But this summer it shall be a priority. Based upon values from the literature, I expect a success rate between 75 and 100%. I'll explain how I arrived at that range in the next section. Even if we have to fall back on bulbil regeneration alone, which has a success rate between 40 and 50%, we could still test enough plants to acquire a virus-free nuclear stock and manage it that way. But again, the goal is to produce an arbitrary number of virus-free plants even from infected stock and without resorting to tissue culture. I insist upon a fast, economical way of clearing a wide spectrum of common viruses. Now that you understand the overall process, for the rest of the video I'm going to explain some of the key steps. We shall begin with the electrophoresis setup. We need a 200-watt power supply, a Pyrex tray, agarose, stainless steel wire, and baking soda. This is not unlike making Jell-O. We boil some water and add the agarose. We'll also need an electrolyte so our gel conducts electricity. For that, we'll add 0.1 grams per liter of baking soda. I use a smaller tray inside the larger tray to serve as a mold. Set the electrodes in both ends of the tray and pour the warm agarose mixture. When solidified, remove the smaller tray carefully and it's ready to use. Next, we need electrolyte solution. To some distilled water, add the same amount of baking soda as before, 0.1 grams per liter, and mix well. Load the chips into the well and add electrolyte solution to the top of the mold. Put plastic wrap over top to keep everything submerged. Hook up the power supply. Normally, there is a specific polarity in electrophoresis procedures, but in this case, either lead to whichever end will do. Set the current to 20 milliamps and turn on the power supply. After 20 minutes, turn off the power, disconnect the leads, and remove the chips. After a rinse, they're ready for the next treatment, silver nanoparticles. Silver nanoparticles are central to this process. They can be produced in various sizes and configurations, such as rods, spheres, pyramids, and cubes, depending upon the reaction conditions. I chose spheres of the smallest possible size, and my production method is customized for that objective. Normally, I make 4 liters at a time in this big flask because we use a lot of solution. But when we are busy propagating, I do not have time to make movies. So today, we're going to mix up a smaller amount, 1 liter, in this smaller flask. First, we have to degas the water. Although we always start with distilled water, which contains no dissolved salts or minerals, it does contain dissolved gases. Upon exposure to air, a certain amount of oxygen, nitrogen, and carbon dioxide are absorbed by the water. Carbon dioxide in particular reacts with the water, forming carbonic acid. For successful production of silver nanoparticles, however, these gases and carbonic acid must be removed. There are a number of synthesis methods for silver nanoparticles, but only one paper referred to this step, and I find it to be critical. Gases become less soluble in water as the temperature increases, and carbonic acid breaks back down into carbon dioxide as well. So to get rid of dissolved gases, we boil the water. As we heat the water, we'll flush atmospheric and expelled gases with a little bit of argon. After the boiling has peaked, we turn off the heat and let the temperature drop a few degrees. At that point, it helps to increase the flow of argon and pull a slight vacuum a few times. This removes the rest of the gases. Decrease the argon flow to a trickle and let cool to about 50 degrees Celsius. To get the very finest silver particles in solution, we'll start with a silver salt, silver nitrate. Our reaction is as follows. 2 silver nitrate plus 2 sodium borohydride gives us 2 silver atoms, hydrogen, borane, and sodium nitrate. Hydrogen and borane are gases, so they bubble out of solution. What's left is atomic silver and, conveniently, sodium nitrate, a rapid action fertilizer. So we need 2 ingredients, but we must also add 2 stabilizers, which prevent aggregation of the silver into larger and larger particles, and eventual precipitation. To avoid instant aggregation, we add trisodium citrate, and for long-term stability, we add a gracious amount of polyvinyl pyrrolidone, or PVP, which may be thought of as molecular spaghetti. It increases the shelf life of silver nanoparticles from hours to months. Now that the water has cooled, we set some aside for the sodium borohydride solution, which must be prepared separately and used immediately. We also save a little bit for topping off at the end, arriving at precisely 1 liter of solution. We measure the silver nitrate, sodium citrate, and PVP and add them to the flask. Adjust the pH to 6.0 with acetic acid and set the pot into an ice bath to cool it down further. Chill some of the degassed water in ice. Quickly measure the sodium borohydrate and add it to the beaker. Transfer the sodium borohydride into a separatory funnel and add it dropwise under vigorous stirring. The solution will turn black upon contact, but eventually settles upon a dark coffee brown and fizzy. This is the hydrogen and borane gases coming off. And after 10 minutes of stirring and cooling, top off to 1 liter and transfer to brown bottles for storage. Although the solution is dark, upon dilution it's a beautiful daffodil yellow. We dilute this by half, which is still quite dark, and submerge the chips in it for 12 to 24 hours. Chips treated with this combined method must also undergo bulbil regeneration, which itself results in virus-free plants a certain percentage of the time, perhaps 40 to 50%. So by applying the success rates of the individual methods to this combined approach, we can calculate a theoretical success rate. Using reasonable values from the literature for each individual method, we arrive at about 83.5%. I'll have a good idea of the actual success rate next summer. I'm hoping for synergistic effects at a rate of 100%. Can we have that? But again, I'll settle for any success rate that we can manage. So why do it? Why all of this fuss about viruses in Narcissus? Most of the time we don't see the symptoms anyway. Well, if we are going to produce the finest daffodils in the world, they have to be more than just rare and exquisite. They have to actually be the finest daffodils in the world. I want daffodils that grow the way they were intended, with nothing holding them back. Longer stems, more flowers, and faster division. It's what we all want. In addition to that, dozens of old cultivars are no longer available because they've been lost to viruses. Examples include Peeping Tom, Irene and Mary Copeland, and Katie Heath, as well as Madame de Graaf, Bahama Beach, and many others. These are great daffodils, and if no one does anything, they won't see the market again. This process gives us an opportunity to bring back all of these great flowers. This year, we harvested about 240 cultivars from Joe Ham's garden. Everything is chipped, treated, incubated, and planted. Each variety goes into a dedicated planter in an area we call Ham's Way. 320 new planters were installed this year, for a total of 840 beds. I currently have about 300 of my own seedlings in cultivation. They're being put through the process to find out which ones can handle being farmed and how they perform overall. We might see some of those next year. Managing a website is always a thing, and it's hard enough keeping up with the changes in technology that keep happening and fixing bugs. But I'm very excited about some things that are in the pipeline. I don't like to make premature announcements, but I will say this. There are 2 new services coming to daffodils.com that my customers will really enjoy. When the time is right, I'll post a message on DaffNet. Again, my name is Matt Duddy, and thank you for having me. I had fun making this video. I'm going to turn the floor back over to myself and the ADS Fall Forum for your questions. I hope you enjoyed.